Hello there, welcome to my channel on chemistry lessons. Predominantly it focuses on AQA A-level, but it also covers the BTEC Applied Science specification as well. The aim in this series of videos is to be as interactive as possible and to offer you opportunities to practice your questions as we go as well, and for me to go over and explain them. So please don't forget to subscribe so that you don't miss out on those blockbuster premieres, so you can be first on there to see them, and also use the comments features to let me know what you think and any videos that you'd like me to upload and add. Sorry, I'll take my mask off. So this is lesson 3. It looks at the pH of weak acids. Lesson 1 was looking at definitions and the pH of strong acids. Lesson 2 was looking at the pH of strong bases and using the Kw constant. So this is weak acids then, and it's equilibrium-y. There's an awful lot of, you need to understand your equilibrium in order to be able to do this and understand this topic. So let's remind us of what's going on then. So in lesson 1 we saw that weak acids partially dissociate or slightly dissociate, and we can see this with the equilibrium shown here. HA being an acid, we know that acids contain H, and the A is just the rest of the acid, if you like. And it will slightly dissociate to H plus and A minus, shown by that equilibrium sign. And we could quite feasibly show an equilibrium constant value for that equilibrium. You'll have to remind yourself of equilibrium from first year. But the Kc value would be the H plus concentration multiplied by the A minus concentration all over the concentration of HA. And this is called the acid dissociation constant, okay? Because here we're looking at the acid, so it's Ka instead of Kc. It's the same thing. It's the same rules apply, exactly the same rules apply. It's just because it's a weak acid, we call it the acid dissociation constant instead of the equilibrium constant. The same rules apply for equilibrium in terms of shifting right, shifting left, changing conditions, etc. So you do need to remind yourself a little bit of what equilibrium values stand for. But ultimately, a larger equilibrium constant means the equilibrium lies further to the right. So weak acids will have slightly different Ka values from each other because they're not all the same strength. Some weaker acids are weaker than others and some are stronger than others. But the definition of weak means they partially dissociate. So if a weak acid has a slightly higher Ka value, that means it's a slightly stronger weak acid. Hopefully that kind of makes sense. So what you're going to do, pause the video and see if you can write expressions for Ka for the following 4 acids. So you've got 4 weak acids there. You're going to come up with the equilibrium constant or the acid dissociation constant. Okay, so the first one, I suppose what we could do really, if you want to, for the first one I'll do the equilibrium. So I'll show you what's happening. In your weak acid, it's the carboxylic acid proton that is lost. It's that OH proton at the end that is lost. So to do the acid dissociation constant, so Ka for the first acid is H plus concentration multiplied by C4H9COO minus concentration all over the concentration of C4H9COOH. That's your acid dissociation constant. And for the second one, it's H plus concentration multiplied by CH3COO minus concentration all over the concentration of CH3COOH. And then the third one, Ka, is equal to H plus concentration multiplied by C2H5COO minus concentration all over the concentration of C2H5COOH. And then the last one, the Ka value, is the H plus concentration multiplied by the C6H5COO minus concentration all over the concentration of C6H5COOH. H. Notice how they're all square brackets. That's important. The brackets are square brackets for the Ka values because that is showing you that it's a concentration in moles per decimeter cubed. So all we're doing there is we recognize the equilibrium and we're doing the equilibrium constant, which is given the term Ka as the acid dissociation constant. Okay, so what's the point in knowing this Ka value then? What's the point? So why do we want to know this Ka? Well, if we have an expression for Ka, Ka includes H+. And we know that H+ is our key to working out the pH. So if we have the acid dissociation constant, there's a way for us to be able to work out the pH because we can find H+. Now let me try and do some explaining as to how that works, and we'll do some practice on that. Now, if we think about equilibrium, let's just use the terms X and Y. So at the start of a weak acid, we've got Y amount of HA. So we've got Y moles of HA. And we'll have 0 moles of H+ and 0 moles of A-. Once equilibrium is established, we will have X moles of H+ and X moles of A-. They will dissociate in a 1-to-1 ratio. It's a monoprotic weak acid. So the moles of H+ will be the same as the moles of A-. And the moles of Y will have decreased by X moles. So the concentration of, the moles of HA will be Y minus X. And H+ will be X and A- will be X. So our equilibrium constant, we would have to convert into concentrations, but it would be X multiplied by X divided by Y minus X. And actually, because these weak acids only very slightly dissociate, the equilibrium lies massively to the left. So my argument here is the difference between 0 and X is significant because it's only a small, despite the fact it's a small increase, the percentage increase is significant from 0 to X. However, the decrease from Y to Y minus X is insignificant. And the analogy I use with my students in class is, imagine these were bank balances, okay? Now, equilibrium lies massively on the left. The value for HA is significantly bigger than H+ and A-. So this could be Bezos' bank account is Y, and my bank account is 0. Not far from the truth, if I'm honest. But then allow equilibrium to establish, and Bezos dissociates by 5 million quid, and he puts 5 million quid in my account. I'm going to notice that change from 0 to 5 million. However, Bezos going from however many gazillion billions he's got, losing 5 million, he genuinely wouldn't even notice. So my argument here is Y is pretty much the same as Y minus X. Because losing a small amount from a large amount, you don't even notice it. Okay? So therefore, the acid dissociation constant is X squared over Y, which is the concentration of H+ squared, because the concentration of H+ will be the same as the concentration of A-. So you can see where we're going with this. We can now rearrange this equation to get H+ squared is Ka multiplied by HA, and then we could do the square root of that. So we have an expression for Ka now in terms of H+ squared over HA. That allows us to rearrange it to get H+ concentration is equal to the square root of HA multiplied by Ka. Now in my experience here, people tend to make calculator errors. So when people seem to think they know what they're doing, but they will make mistakes with calculus. So it's worth to practice as much as we can. And just a reminder then of the important things that we've come across so far in the 3 lessons. We've got an expression for Ka, we can rearrange Ka to get H+ concentration, which is good because we can then use the minus log of H+ to get the pH. That allows us to get the pH of a weak acid. We also know that the H+ concentration is 10 to the minus pH, and also there's a Kw value that we use if we want to work out the pH of a strong base. And I've kind of summarized these 3 lessons so far in this little flow diagram. I think it looks very nice if you ask me. But maybe spend some time pausing the video on this page and having a look at what I've done there. But I'm trying to kind of logically break down how you calculate pH. So the only way to calculate pH is from the H plus concentration. The only way. And it's how we get to the H plus concentration is the first thing you need to do when determining pH. Now it's quite easy when you've got a strong acid because the H plus concentration, if it's monoprotic, is just the same. If it's diprotic, you've got to double it. But that's an easy way to find the pH. The base was slightly more complicated. You had to use Kw. Again, go back to video 2. And today we're looking at the pH of a weak acid. So it's more complex, this one. Of course it is. You're using a Ka value, and you're then using Ka H plus squared over HA, and then you're calculating the H plus concentration. So let's have a practice. I'm going to suggest you pause the video for a few minutes, then you have a go at doing this one yourself, and then I'm going to explain this one for you. Okay, or should I say OKA? Sorry, bad joke. Right, so we've got CH3, COOH. We know it's a weak acid, so we know it's going to partially dissociate. That's a terrible sign. It's going to partially dissociate CH3, COO minus plus H plus. We know it's going to do that. So we can come up with an expression for Ka. Concentration of CH3, COO minus, multiplied by the concentration of H plus all over the concentration of the acid. Now, we know a value for Ka. We know that this is equal to 1.74 times 10 to the minus 5. Notice how it's a very small value, and that makes sense, okay, because it's such a small value that equilibrium lies massively on the left, and Ka values will always be small. And we've got a concentration of the acid. So we know that this value here is 0.105. So what I'm going to do is I'm going to multiply 1.74 times 10 to the minus 5. I'm going to multiply that by 0.105, and that's going to be equal to CH3, COO minus, multiplied by H plus squared. We also know that these two are equal, so it's H plus squared, because the concentration of this is the same as the concentration of this, because it dissociates in a 1-to-1. So what I'm going to do is I'm going to go 1.74 times 10 to the minus 5. I'm multiplying that by 0.105. I've got an answer, and I'm going to square root my answer to get H plus concentration, because my answer there is H plus squared. So if I square root my answer, and that comes out at, so I've got my H plus concentration here as 1.352 times 10 to the minus 3. And then I can now put that into minus log the base 10 of 1.352 times 10 to the minus 3 is equal to, so my pH now is equal to 2 decimal places, 2.87. Thank you very much. No, you're too kind. Okay, moving on then. Oh dear. pKa. Maybe just have a think about that question, and then if you want to unpause, I'll talk to you what a pKa is. And then you can pause again and try and do the question. Right, pKa, so the relationship between pH and H plus is minus log H plus. It's the same for pKa. pKa is the minus log of Ka. The reason being for this is that Ka values tend to be very small numbers, and a logarithmic scale is a good way of making very big or very small numbers kind of more manageable, I guess. So we can use this to rearrange. And just to remind you that H plus concentration was 10 to the minus pH, and therefore Ka is also equal to 10 to the minus pKa. So maybe just pause the video again and see if you can calculate the concentration here. Okay, so the first thing I'm going to do is I'm going to find the Ka value by doing 10 to the minus pKa, which is minus 2.89. So that's going to be my value for Ka. Hopefully it comes out at a small number. Right, okay, so 10 to the minus 2.89. So I get a value here of 1.288 times 10 to the minus 3. That's my Ka. And it wants me to find the concentration of the acid. So let me come up with an expression for Ka. Then Ka is going to be the H plus, and in this case I can use H plus squared. And that's going to be over concentration of CH3, CH2, COOH, which is what I'm trying to find. I want to find this, okay? Now if I rearrange this, bring this up here and bring Ka down, I'm going to end up with concentration of CH3, CH2, COOH is equal to the concentration of H plus squared divided by Ka, which I've already said is 1.288 times 10 to the minus 3. How do I find H plus squared? Well, I know that H plus is 10 to the minus pH, and I know pH is 2.5, so I'm going to find out what the H plus concentration is here by doing 10 to the minus 2.5. So my H plus concentration is 3.162 times 10 to the minus 3. So I'm going to square that and then divide by 1.288. So I've just done that now, and I'm going to divide it by 1.288 times 10 to the minus 3. I've got a value here of 7.764 times 10 to the minus 3, and that's in moles per decimeters cubed. And I want it in milligrams per decimeters cubed. So I've got to turn from a moles to a mass. So I'm going to times that by the MR. 36, 37, 38, 39, 40, 41, 42. Plus 32. So I've worked that out as 0.574 grams. So I've now got 0.574 grams per decimeter cubed. Turn it into milligrams is 574 milligrams per decimeter cubed. 574 milligrams per decimeters cubed. Quite complicated and quite complex, okay, but quite happily you'll go through this a couple of times, rewind the video and go through this a couple of times and make sure that you're aware and you can follow what I've done there. Moving on then, so see if you can work your way through this one and then unpause the video and we'll go over it. Okay, so here we don't know what the acid is, we just know it's HA, but the expression for the dissociation will be H plus plus A minus, and we've got the equilibrium sign because we know it's a weak acid. We know that Ka is equal to H plus multiplied by A minus all over concentration of HA. Now if you're asked for the expression for Ka, that's what we must do. So it's tempting to put H plus squared, but that's not accepted in exams as an expression for Ka. That's the expression for Ka. Yes, we have used H plus squared, but that's when we're doing the calculations because we now know at that point that they are equal. But in an exam, if you're asked for the expression for Ka, leave it as H plus and A minus, whatever that A minus may be. And we know that the pH is 4.1. That means we can determine the H plus concentration from this, which is 10 to the minus 4.1. which is, on my calculator, 10 to the minus 4.10 is equal to, so the H plus concentration is 7.943 times 10 to the minus 5. So we know the H plus concentration. We also know that the A minus concentration will be equal to the H plus concentration. So they're both 7.943 times 10 to the minus 5. We also know what HA is, so we can find Ka now. Ka is going to be 7.943 times 10 to the minus 5, and I'm going to square that, divided by 0.0120. Okay. Let me just put that in the calculator. And I have an expression for Ka. It is 5.2. How many decimal places are significant? I'm going to go 3 significant figures here because I've got 3 significant figures in the concentration, and I suppose 3 significant figures in pH, although pH is usually decimal places. But I've gone for 5.26 times 10 to the minus 7. Yes, it's correct. Well done. Right, so a couple of questions ago, we came across pKa. So I'm just going to formally kind of explain this now. Now, Ka values are very small, typically 10 to the minus 3 to 10 to the minus 5, which is quite a big range and very small numbers. Now, the bigger the Ka, the stronger the acid, because it's an equilibrium constant. The higher the equilibrium constant, the further to the right equilibrium lies, and therefore the stronger the acid, because it's dissociating further. pKa is often used instead of Ka, and that's just because it makes the numbers more manageable. So it makes the small numbers more manageable, just as we've seen with the H plus concentration and the pH. The bigger the pKa, the weaker the acid, because as Ka increases, pKa is going to decrease. So it's not what you'd expect. So the bigger the Ka, the stronger the acid, and the smaller the Ka, the weaker the acid. The reverse is true for the pKa. If you don't believe me, have a play about with your calculator and find out. But a large pKa means a weaker acid, and a small Ka means a stronger acid. And that's how you can convert between pKa and Ka, just as you did with pH and H plus concentration. Right, let's move on to some exam questions then. So you know the drill. Pause the video, have a go at the questions, and when you're ready to go through them, unpause the video. Okay, so the first thing is they're trying to confuse you by, or put you off balance by, using a pretty complex sounding 2,4,6, who do we appreciate? No, sorry, 2,4,6 trichlorophenol. I don't really care its name. We are told it's a weak monoprotic acid. So as far as I'm concerned, it could just be called Derek. I don't really care. It's a weak monoprotic acid, which means it dissociates to produce 1 moles of H plus and A minus, but an equilibrium, it's weak. And we're told that the Ka value is 2.51 times 10 to the minus 8. So it's very, very weak. And we know that that is equal to H plus multiplied by A minus divided by HA. We're given the concentration of Derek. It's 2 times 10 to the minus 3. And we know that H plus and A minus will have the same concentration because they dissociate in a 1-to-1 ratio. That will always be the case. We'll only ever look at monoprotic weak, at weak monoprotic. So I'm going to have H plus squared is equal to Ka, which is 2.51 times 10 to the minus 8, multiplied by the concentration of Derek, which is 2 times 10 to the minus 3. And then I'll square root that value. Okay, the answer comes out at 7.09 times 10 to the minus 6. So the answer is B. Moving on to question 2 then. We've got some pKa values. Now, a high pKa means a low Ka and a weaker acid. So the butanoic acid has a lower pKa and a higher Ka. So this is the strong acid. So which is true? Propanoic acid is stronger. That's not true. The the value of Ka is greater. Well, for the stronger acid it would be greater. So actually no, that's also wrong. The value of Ka, okay, well the only way I can work these two out is by doing 10 to the minus 4.87 and 10 to the minus 4.82 to see which one is correct, and C is the correct answer. Okay, question 3 then. So you know the drill, pause the video, and when you're ready to go through the answer, we'll go through it. Should take about 10 minutes this. Okay, so first off then is just your standard definition for an acid, which is proton donor. Nice easy start to the exam question. Write an expression for the acid dissociation constant Ka of ethanoic acid. Right, so we should know that ethanoic acid is CH3COOH, that's ethanoic acid, and the acid dissociation constant will be H plus concentration, so square brackets H plus, square brackets CH3COO minus, all over the concentration of CH3COOH. Now, if you've put on the top concentration of H plus squared, you are wrong, okay, because that's not an expression for Ka. It's how we calculate pH, and we use the fact that they are the same. But when you're asked for the expression, you can only do, there's only one correct answer, and it has to be as I've shown there. The only variation would be if you just put these two the other way around. Okay, so now we're given the value of the Ka, and we've been given the pH. It wants us, so we're going to use this expression, we're going to rearrange it. We're going to get concentration of CH3COOH, which is what we've been asked to find. That's going to be equal to the concentration of H plus multiplied by the concentration of CH3COO minus, all divided by Ka. So I've just rearranged our expression for Ka to get what we require, which is the concentration of the ethanoic acid. Now I'm going to use this value here. So we've got a value for Ka, that's fine, we've got it in the question, 1.75 times 10 to the minus 5. We don't have any value for the H plus or the CH3COO minus, but we do have pH. So we're going to calculate the H plus concentration by doing 10 to the minus 2.69. And if you put that into your calculator, you end up with 2.042 times 10 to the minus 3 moles per decimeter cubed, and these two are equal to each other this time. So we can do 2.042 squared divided by 1.75 times 10 to the minus 5, and that gives us our answer of 0.238 moles per decimeter cubed for your concentration of ethanoic acid. Right, moving on to C. We've got chloroethnic acid, and they're telling you what it is. So it's pretty much the same as ethanoic acid. Instead of one of the H's on the first carbon is a chlorine. And you've been given the acid dissociation constant, which is slightly, well, a fair bit higher actually. It's 1.38 times 10 to the minus 3 as opposed to 1.75 times 10 to the minus 5. And it wants an equation for the dissociation of chloroethnic acid in aqueous. So okay, so what's going to happen? ClCH2COOH, the dissociation in aqueous, so we could put plus H2O. It's weak, so it must be reversible. ClCH2COO minus plus H3O plus. So we could do that because it's asking for the dissociation in water, or we could just have the dissociation without the water and just have it as H plus. Both will be accepted. And it's asking us to suggest why. So when you see the term suggest, that does mean that you've not been taught it, but you've got to try and use knowledge or things that you have been taught to apply it here. So for some reason, it's a stronger acid when it's got a chlorine instead of just a hydrogen. So think logically, what's happening? So the fact that it's a stronger acid means that this proton is being released more readily or more easily. Why might that proton be released more readily or more easily when you've got a chlorine here instead of a hydrogen? Well, the chlorine is electronegative. The chlorine is drawing electrons towards itself, which means that proton can be more easily released. So there's your 2 marks. Because chlorine is more electronegative and it's electron withdrawing or electron pulling, it means that that proton is more easily donated. Now you might think, how was I supposed to know that? But actually the question's telling you the proton is more easily donated. You've just got to come up with a logical explanation as to why. And the fact that chlorine is more electronegative, that's your way in. Okay, so final question, question 4. It's quite a long question this. It's a 20 marker, so I've split it into 2 slides. So you know the drill. It should take about somewhere near 10 minutes on this page, and when you're ready to go through it, unpause and we'll go over it. Okay, so we've got nitric acid, HNO3 is a strong acid, knew that anyway. And ethanoic acid is a weak acid, knew that anyway. It says write an equation to show how ethanoic acid behaves as a weak acid in its reaction with water. So we have to show it reacting with water, but showing it as a weak acid. So its reaction with water is to donate the proton to water. And the key point that we've done here is the reversible sign. That's the weak, the term weak. There we go. So with water, the water will act as a base and the acid will act as a weak acid, and it's reversible. When pure ethanoic acid reacts with pure nitric acid, ethanoic acid acts as a base. Write an equation for this. Okay, so we've got HNO3, which is nitric acid. We've got ethanoic acid, CH3COOH. And what's going to happen is the nitric acid is acting as an acid and donating a proton, and your carboxylic acid is acting as a base and accepting a proton. So we're showing the acid losing a proton and the ethanoic acid gaining a proton. Right, calculation time. So calculate the pH formed when 50 centimeters cubed of distilled water was added to beaker A. So beaker A is 100 centimeters cubed of nitric acid. So we've diluted it. So what we need to do is, if we find the moles of H plus from the nitric acid, which will be concentration times by volume. Don't forget to divide your volume by 1,000 because it must be in decimeters. So I have that on my calculator as 1.25 times 10 to the minus 3. And now I'm going to find the H plus concentration, which is the moles over volume. So we've just worked out the moles, and the volume now is 150. So it's 150 over 1,000. That's the H plus concentration, which I have as 8.33 times 10 to the minus 3. And all we need to do now is work the pH out, which is minus log of H plus, so minus log of 8.33 times 10 to the minus 3 comes out 2.08. Must be 2 decimal places, look. That's 2 marks. 4 marks for the next one though, so there's obviously an awful lot more going on here. So calculate the pH of a solution formed. We've got 50 centimeters cubed of sodium hydroxide added to beaker B. Okay, well we already know the moles of H plus from beaker B, because it's the same as beaker A. So the number of moles of H plus is 1.25 times 10 to the minus 3. And we're adding a base to it. So let's find the moles of the base. The moles of OH minus, it's 50 over 1,000 times by 0.0108, which I have as 5.40 times 10 to the minus 4. So looking at the moles of H plus, looking at the moles of OH minus, be careful that it wasn't mono, that it was monoprotic and monobasic and not dibasic, diprotic. Remember videos 1 and 2, be careful with your number of moles. It is monoprotic and monobasic. So now I'm looking at the moles of H plus and moles of OH minus. Which one's in excess? This one. So I'm going to find out how much it's in excess. So 1.25 times 10 to the minus 3 minus 5.40 times 10 to the minus 4. So when I'm saying excess, it's the bigger of the two numbers. There's more H plus than there's OH minus. So my moles of excess is, I worked that out as 7.10 times 10 to the minus 4 moles of H plus. So that's your excess. So excess is 7.10 times 10 to the minus 4 moles. I'm now going to work out my concentration of H plus, which is moles over volume, which is 7.1 times 10 to the minus 4. The new volume now, it's 50 and 100. So again, it's over 150 times 10 to the minus 3. That's going to give me a H plus concentration, which I have as 4.73 times 10 to the minus 3. Now turn that into a pH, which is minus log of 4.73 times 10 to the minus 3, and I get 2.32. Final answer, 2 decimal places. If you've got 2.33, it's correct as well. It just means that you've done some rounding at some point. So 2.33 would also gain all 4 marks. Okay, final part of this question then. So you know the drill by now. Pause the video, have a go at the question, and when you're ready to hear the answer, unpause. Expression for Ka for ethanoic acid, concentration of H plus multiplied by the concentration of CH3COO minus all over the concentration of CH3COOH. Only accepted answer. Now, being asked to calculate the pH. So I'm going to rearrange this formula. Okay. Now, the first trick we do though is we can use H plus squared over CH3 COOH. And then we Ka multiplied by the concentration of CH3 COOH equals H plus. If I square root the left hand side, there we go. So H plus is equal to the square root of Ka multiplied by CH3 COOH. We know the Ka value, we're given it in the question. We're also given the concentration of the acid. So we're going to do 1.74 times 10 to the minus 5 multiplied by 0.0125 equals square root. That will give us the H plus concentration, which I get as 4.66 times 10 to the minus 4. And then we'll do pH is equal to the minus log of 4.66 times 10 to the minus 4, which gives me 3.33. There's 4 marks. Part 2. Aqueous sodium hydroxide is added to beaker C until the pH of the solution becomes 4.84. Name the salt formed when ethanoic acid reacts with sodium hydroxide. That's going to become sodium ethanoate or sodium ethanoate. Sodium ethanoate. Simply, whatever the acid is, instead of oic, it becomes O8. So that's O8 salts. And because it's sodium metal, it'll be sodium ethanoate. Now, this is quite tricky. Calculate the ratio of the salt to the ethanoic acid. You might not even know where to start here, okay? Because they've been a bit awkward with the terminology. So let me just make some space on this slide here. Right, let me just go back to the expression for Ka. There we go. Well, this is the salt here. The salt is this O8. And we want salt over ethanoic acid. So what we need to do is get an expression of CH3 over. So what we need to do, if we divide both sides by H plus, we'll end up with CH3 COO minus over the acid. And that is the ratio they are asking for. This is the salt and this is the acid. So they want the ratio of the salt over the acid. So what we actually need to do here is the Ka value divided by H plus. Now, we know the Ka value because we've been given it in the question, which is 1.74 times 10 to the minus 5. In terms of H plus, we're told the pH is 4.84. So H plus concentration is going to be 10 to the minus 4.84 because H plus concentration is 10 to the minus pH. That comes out at 1.45 times 10 to the minus 5. So if we do 1.74 times 10 to the minus 5 divided by 1.45 times 10 to the minus 5, that's going to give us the ratio of the salt to the acid. Now that was a tough question. You probably didn't know where to start there, perhaps. That was tricky because of the way in which they've asked it. Okay, explain why chloroethnic acid is stronger. We saw this earlier. So the reason being that the chlorine is electronegative. It draws electrons towards itself. And what that does is the OH bond in the acid becomes more polar. So the electrons are pulled more towards, so that effect of having a chlorine drawing the electrons through makes this OH bond more polar and the proton more likely to be donated. So your 2 marks come from the chlorine being electronegative and drawing electrons towards itself, and the second mark for making the OH bond weaker and allowing those protons to be released. And F, explain why data books do not usually contain values for Ka for strong acids. Well, that's because strong acids fully dissociate and therefore don't require or don't have equilibrium constants because they fully dissociate. And that's it. So hopefully you made it to the end. This is a long one. I appreciate that. We're up to 90 subscribers at the moment. And once we get to 100, I'm going to give away a free signed periodic table to one of my lucky followers. So stay tuned.